Now the problem number 2 also very easy. Don't you have to consider the salt hydrolysis? Apparently it is a salt, and there you have to consider salt hydrolysis equation that you have to remember. But I will do consider here A minus is a base, weak base. See, number 2. I will do consider A minus is a weak base, and Na plus comes from the strong part. It has no effect with respect to the change of pH since it will not undergo hydrolysis. They are inert ion. Actually, counter ion of a strong component are inert ion with respect to pH. Now, A minus if I do consider is a weak base, then I will use the formula POH is equal to half pKb. Now the question is, what is the pKb of A minus? That I have discussed. Now, I have discussed it. That is pKa plus pKb is equal to 14. That means its pKb is equal to 14 minus 5. 14 minus 5, that is equal to 9. Easily you will get from this. And additionally, it will be given. If it is given, you will easily get pKb of conjugate base. That means half into 9. Half into 9. Okay. Now minus half log C means 10 to the power minus 1. I have taken here 0.1 just for easy calculation. Now it is 4.5 minus plus 0.5. You got there 5, and pH you will get 14 minus 5. That is 9. pH is 9 basically here. Weak base. Thank you students, and thank you AKADIMOS for inviting me here for online class. Today I am going to discuss a part of ionic equilibrium. You know equilibrium associated with ions, that is ionic equilibrium. When weak acid, weak base, they will undergo dissociation in aqueous solution. A part of acid or base will undergo dissociation, and that dissociation is equilibrium dissociation, not their 100% dissociation you will get. But for a strong acid and a strong base in dilute solution, they will undergo 100% dissociation. The part you know, when weak acid in water or weak base in water, you know solvation energy is the driving force of dissociation of water. For example, I am taking here a weak acid HA, taking water and its dissociation, partly undergo dissociation, and you will get H3O plus A minus. And this dissociation is an equilibrium. It will follow a mathematical restriction, that is equilibrium. And you know equilibrium constant. Here the dissociation equilibrium constant of acid only function of a temperature. Now, for simplicity, you can eliminate water from both sides. Simply you can write here HA reversible H plus A minus. Now initial concentration of HA you have taken C. Let alpha is the degree of dissociation at equilibrium. Degree of dissociation means fraction of dissociation at equilibrium. Then at equilibrium the concentration of HA is C into 1 minus alpha. H plus is C alpha. This is C alpha. Alpha is the degree of dissociation. Now the dissociation equilibrium constant of acid, let it is Ka. Then Ka, what you can write? Ka is equal to C alpha into C alpha divided by C into 1 minus alpha. One C will be cancelled out, and the equation of Ka in terms of alpha and C, that is Ka is equal to alpha square divided by 1 minus alpha into C. Now see the equation. K is an equilibrium constant, and you know any equilibrium constant only function of temperature, not depends on other external condition. Now C concentration. If you decrease C decrease, that means you are diluting the solution of HA. With increase of dilution, C decreases means with increase of dilution. If it will decrease, since Ka constant, to maintain Ka constant, alpha square by 1 minus alpha must be increases. since Ka constant. And alpha square by 1 minus alpha value increase if alpha increases. That means with increase of dilution, alpha, that is the degree of dissociation, that is the fraction of dissociation at equilibrium, increases. Now when C tends to 0, C tends to 0 is called infinitely dilute. You know in science the term infinite is meaningless, but remember when we are discussing about the infinite dilution, but practically it is finite. In solvation, with respect to solvation energy, when the solvation energy becomes constant, and that dilution is the infinite dilution practically. So when C tends to 0, mathematics will tell you then alpha tends to 1. So alpha tends to 1 means there occurs 100% dissociation of HA, like strong acid. No molecular form of HA you will get. This is Oswald dilution law. With increase of dilution, degree of dissociation increases, and when C tends to 0, that is infinitely dilute, then all acid becomes strong acid. That means all acids will undergo 100% dissociation. Now, generally in our case, special case is different. Alpha generally very less than 1. If it is very less than 1, this is important. When we will consider alpha is very less than 1. Remember when Ka value, remember this thing, less than 10 to the power minus 3. Ka value less than 10 to the power minus 3, that means 10 to the power minus 4, minus 5, and C 0.1 maximum. If C becomes more dilute, then remember alpha increases. There you can't neglect alpha with respect to 1. That is special case. If time permit, I will discuss. Now 1 minus alpha, you can consider it is very close to 1. In 80% our case, alpha you can neglect with respect to 1. In JEE advanced some problem came already. There you can't neglect that alpha with respect to 1. There alpha you will get a considerable value. Now, but JEE mains, medical, board exam, their 100% alpha is negligible with respect to 1. Then what expression you will get? Ka equal to alpha square C. Remember this equation, K equal to alpha square C. And this equation you will get in also salt hydrolysis, that I will discuss. And alpha is equal to, you will get root under Ka by C, equilibrium constant by C. Here you will get a qualitative idea how alpha varies with C. With increase of dilution, alpha increases. Now concentration of H plus, that you know, C alpha, C into alpha, and alpha you know root under K by C. If you put this, then you will get Ka into C. These three equations, remember. Alpha is equal to this, and since this form of equation is applicable in all, and concentration of H plus is equal to root under K into C. Now both sides you can take minus log. If you take minus log in this equation, like concentration of H plus is equal to root under Ka into C, this equation you got. Both sides take minus log, then you will get left side pH, minus log of H plus and concentration pH, and right side you will get half pK, minus log of K is called pK. pK is the properties of weak acid or Ka. Higher the Ka, lower is the pK, minus half log concentration of acid. So this is the formula by which you will get pH of the solution when there are weak acid in water, pure weak acid in water. That means concentration of these and these are equal, no additional A minus from the outside, no additional H plus from the outside. Then pure weak acid in water, you will get pH by using this equation, by considering alpha too much less than 1, 1 minus alpha equals to 1. That means this equation by taking approximation alpha is negligible. Similarly, if you take base, similar equation you will get. If you take base, weak base like ammonium hydroxide, you will get similar equation. See, if there are a weak base BOH and it will undergo partial dissociation to B plus and OH minus. Of course, the solvent is aqueous. You know, here the pH term always with respect to the solvent. Water, acid, base, strength, always the leveled solvent is water. Acid are those compounds which are more acidic than water, and base are those compounds which are less basic than water, less acidic than water with respect to water actually. Now, BOH, similarly here also you will get this is C1 minus alpha, this is C alpha, and here the equilibrium constant, dissociation equilibrium constant is Kb, alpha square C by 1 minus alpha, same thing you will get. And there also you will get alpha is equal to root under Kb by C, and concentration of OH minus here you will get root under Kb into C, but you know concentration of H plus into concentration of OH minus is pKw, Kw. The Kw, from here you will get concentration of H plus also, or in both side if you take minus log, there you will get POH. POH is equal to half pKb minus half log concentration of base. Here also by neglecting alpha, that is the degree of dissociation of base, neglecting with respect to 1. Similar equation, this equation are similar. For acid it is pH, for base it is POH. And by using these two equation, you will get pH of pure acid in water or pH of pure base in water. Once you got pOH, if you minus from 14, you will get the pH of the solution. Now, the important part here, these two equation is enough to get pH of third hydrolysis also, that I am going to show you. You know A minus, which is the conjugate base of HA. A minus is a base, whatever it may be conjugate base. Conjugate base with respect to HA. That means it is a base. The base, when it will show basic character, the corresponding dissociation equilibrium is this one, HA plus OH minus. This you can say the hydrolysis of A minus, both side Na plus, if the Na plus or K plus, that means the part coming from the strong base Na, both side Na plus will be cancelled out and the ultimate equation you will get this one. Remember, the counter ion of strong base like Na plus K plus and counter ion of strong acid like Cl minus SO4 2 minus, they are inert with respect to change of pH in aqueous solution. Since they are comes from strong component, they will not undergo the hydrolysis. That's why whatever it is, it may be Na plus K plus, no problem. It will not change the pH. Both side Na plus will be cancelled out. Now you can say this is hydrolysis, or you can say it is the properties of basic character of A minus. That means you can say it is Kb of A minus base or KH hydrolysis constant. Better say Kb of A minus, then problem you can easily solve without remembering any formula. You know it is a weak base. It's Kb if you know, then POH you know you will get by using this formula, half pKb minus half log concentration of base A minus. Done. Now the question is, if Ka of HA given, then how you will get Kb? Since remember, Ka of any acid and Kb of its conjugate base are not independent variable, they are related. There you will get mathematical restriction that I am going to show you. It is the Kb of A minus. C Kb is equal to concentration of HA into concentration of OH minus divided by concentration of A minus. Since it is pure liquid, you know activity 1, concentration 1 will take. Now in solution, there you will get H plus. Since there is a mathematical restriction Kw is equal to 10 to the power minus 14 at 25 degrees centigrade, concentration of H plus into concentration of H minus 10 to the power minus 14. That mathematical restriction is valid in aqueous solution, any aqueous solution. That means there must be H plus present, whatever its concentration value. Now you can multiply, since there are H plus present, you can multiply both denominator and numerator by H plus. Then see, this is Kw, this is concentration of H minus into H plus is Kw, and concentration of A minus into concentration of H plus divided by this is Ka. That means it is Kw by Ka, and you got equation Ka of weak acid Ha into Kb of its conjugate base A minus is equal to always Kw. I told you these two are not independent variable. There you will get mathematical restriction Kw, and you know the value of Kw is constant 10 to the power minus 14 at 25 degrees centigrade. It is the function of temperature. Remember, since dissociation of water is an endothermic phenomena, with increase of temperature Kw increases. Now both side minus log you can take. Like pKa of any acid Ha and pKb of its conjugate base. pKb of conjugate base, remember, not any base, conjugate base of Ha. A minus is equal to pKw, that is the 14 at 25 degree centigrade. I'll use this one. Then by using this concept, I will discuss some mathematical problem. For example, there are 0.1 molar, let Ha weak acid given, its pK value given, pK or Ka given. For simple calculation, I am taking it is 5. What is the pH? What is the pH? Yes. And number 2, second problem given, what is the pH of 0.1 molar NaA? Both pH you have to find out. How you will get? Problem number 1 is very easy. By using that formula, here you know pK 5 means Ka 10 to the power minus 5, alpha negligible with respect to 1, and the formula you know pH is equal to half pK. That means half into 5 minus half log C. C means concentration. This is 10 to the power minus 1. Then it is 2.5 plus half. That means you got 3. Very easy. Okay. Now the problem number 2 also very easy. Don't you have to consider the salt hydrolysis? Apparently it is a salt, and there you have to consider salt hydrolysis equation that you have to remember. But I will do consider here A minus is a base, weak base. See, number 2. I will do consider A minus is a weak base, and Na plus comes from the strong part. It has no effect with respect to the change of pH, since it will not undergo hydrolysis. They are inert ion. Actually, counter ion of a strong component are inert ion with respect to pH. Now, A minus if I do consider is a weak base, then I will use the formula POH is equal to half pKb. Now the question is, what is the pKb of A minus? That I have discussed. Now, I have discussed it. That is pKa plus pKb is equal to 14. That means its pKb is equal to 14 minus 5. 14 minus 5, that is equal to 9. Easily we will get from this. And additionally, it will be given. If it is given, you will easily get pKb of conjugate base. That means half into 9. Half into 9. Okay. Now minus half log C means 10 to the power minus 1. I have taken here 0.1 just for easy calculation. Now it is 4.5 minus plus 0.5. You got there 5, and pH you will get 14 minus 5, that is 9. pH is 9 basically here, weak base in water. So by using same formula you can do the salt hydrolysis problem also. Now I want to show a more two problem. Here I have taken weak acid and the salt of weak acid. Now I will take weak base and salt of weak base. Let 0.1 molar ammonia or ammonium hydroxide. Its pKb given, let for easy calculation, pKb let it is 5. And 0.1 molar ammonium chloride, salt of strong acid, both pH. Then here, similarly, here I will consider NH4 plus as a conjugate acid of ammonium hydroxide, and ammonium plus its pK value 14 minus 5 is equal to 9. I will consider, and Cl minus comes from the strong acid, that's why it is inert with respect to the change of pH. Then how we will get is weak base POH is equal to half pKb, half into 5 minus half into log 0.1 log 0.1, and by using this equation you will get POH, and 14 minus from 14 you will get the pH easily. And what is the pH of the second problem? Here consider it is a weak acid, NH4 plus ion, and pH is equal to half pK. Half pK means half into 9 minus half log 0.1. By using this equation directly, you will get pH of ammonium chloride solution. That means you got idea. Additionally, don't you have to remember the salt hydrolysis part. From this equation, you will get the pH, and by taking alpha, that was alpha for weak acid, weak base, and that is in salt, that is H, degree of hydrolysis, and KH, hydrolysis constant. Actually, for ammonium chloride, the Ka of ammonium is the KH of ammonium chloride, hydrolysis constant of ammonium chloride, and alpha of ammonium ion is the degree of hydrolysis of ammonium chloride. They are similar, they are same thing. If there are a problem, let 100 ml 0.2 molar HCl plus 100 ml 0.2 molar acetic acid. If there are this type of problem, this type of means strong and weak, mixture of strong and weak. Here the strong acid and weak acid mixture. And remember, strong acid they will undergo 100% dissociation, and there you will get common ion H plus. And to get pH of the solution easily, don't you have to consider the dissociation of acetic acid. They are just to neglect the dissociation of acetic acid, you will get easily the pH of the solution within 10 seconds. You know, now the HCl concentration, tell me, 100, volume becomes doubled, the solution concentration becomes half dilution, 0.1 molar. I will not consider the acetic acid dissociation due to common ion H plus. In presence of strong and weak will not show acidic character, and negligible. If it will show negligible, don't you have to consider that. Then automatically pH is concentration of H plus 0.1, pH is equal to 1 you will get. The actual value of pH little bit less than 1 due to some H plus from the acetic acid. It may be 0.999998. So don't you have to take exact calculation, since it will take huge time. Just do neglect the weak component, you will easily get the pH of the solution. Similarly, if there are weak base and strong base, just consider strong base. But remember, consider the dilution effect. 0.2 molar HCl after adding this, 0.2 molar concentration will be changed due to dilution. That dilution effect you have to consider to get the exact concentration of strong acid or strong base. Let there are a dibasic acid, 0.1 molar, a dibasic acid H2A given. It is a dibasic acid and partly it has two different equilibrium constant K1 and K2. Overall equilibrium constant K is equal to K1 into K2. Individual K1 always is strong, you know. K1 let it is given 10 to the power minus 4 and K2 given 10 to the power minus 9. First dissociation given H2A reversible HA minus plus H plus. This K1 given here and HA minus reversible H plus and A2 minus. This is K2 given. Now it is C into 1 minus alpha 1. It has C alpha 1, C alpha 1. Here the concentration of C alpha 1, 1 minus alpha 2, and this is C alpha 1 alpha 2, this is C alpha 1 alpha 2. Now concentration of H plus is equal to this plus this, you can take common C alpha 1, 1 plus alpha 2. See, K2 value 10 to the power minus 9. You can easily neglect alpha 2, too much less than 1, then you can, it is C alpha 1. And of course, K1 also 10 to the power minus 4, here also alpha 1 also you can neglect with respect to 1. And you can use that same formula, that is the pH is equal to half pKa minus half log C. But remember, here I will consider K1, I will do neglect the K2, that means you will get half pK1. Take K1, neglect K2, you will get the pH of the solution minus half log C. Put the value, pH is equal to half pK1 means 2 minus half log 0.1. That means you will get 1.5. No, not 1.5, 2.5 plus 2.5. That means you got easily pH of the dibasic by neglecting the K2. If there are K1, K2, K3, then like H3PO4, I do neglect K2, K3 or take only the K1, you will get the pH of the solution. Here I have discussed only if there are weak acid in water or weak base in water, then you will get easily the pH of the solution by neglecting alpha with respect to 1. If alpha is not negligible with respect to 1, there you have to do exact calculation. That means K is equal to alpha square C by 1 minus alpha. Put the value of C, put the value of K, you will get a quadratic equation. And from that quadratic equation, you will get the alpha. And that alpha put in concentration of H plus is equal to C alpha, you will get exact H plus 9 concentration. That is the rare case, you will get some problem in advance. Otherwise, alpha is negligible with respect to 1. But one additional thought I have given here, that is any salt you can consider either it is a weak base or weak acid. Like ammonium chloride, do consider it is a weak acid, ammonium. There, just apply the formula of weak acid, pH is equal to half pKa minus half log C. Like another sodium acetate is a salt, just to consider acetate is a base, weak base. And just apply the same formula, pOH is equal to half pKb minus half log C. That pKb is the pKb of acetate and that pKb is the 14 minus pK of acetic acid. And I told you that Kb of acetate is the KH of sodium acetate salt, hydrolysis constant. And alpha is equivalent to here degree of hydrolysis H. And percentage of hydrolysis you will get by multiplying 100. So by using the weak acid in water or weak base in water concept, you can easily get the pH of weak acid as well as salt, pH of weak base as well as salt. Don't you have to remember multiple formula. Simply you will get pH and pOH. Thank you, students.